Hi guys, and welcome back to another kind of mini lesson for Physics C. So today we're going to be talking about average versus instantaneous. And really specifically, we're going to be talking about velocity here. The reason why we're talking about velocity is because we know that when we're talking about our kinematic equations, we're talking about uniform acceleration. And if there is uniform acceleration, that means our change in A is equal to 0. And when our change in A is equal to 0, we can then say that our A average, I'm going to try writing that again. Our A average is equal to our A. So that's an assumption that we're just making if we know that there's uniform acceleration. Most of the time there is going to be. If there's not, we could apply some of these ideas as well. So we're going to look at two different graphical kind of ideas of how to see this. All right, so this is going to be my x versus t graph, and I'm just going to kind of sketch a parabolic in here, kind of parabolic there for us. So you have learned in prior classes, and I even mentioned this in one of my other videos, that delta x over delta t is equal to v average. Now, you may have actually just learned in your prior classes that delta x over delta t is equal to v. But we're going to be really, really specific in saying that it's equal to the average. So we're going to be looking in at this point here. I'm going to call it some point in time. That is not a good color. So TP, some point in time. And I want to know the velocity of this point. Well, if this is the only definition that I have, I'm going to choose some other points. So let's start with red. I'm going to choose red. I'm going to call this T3. Well, I go ahead and connect those because I know that these are the ones that I'm working on. In order to get there, I'm going to do what this says here. So I'm going to do x3 minus xp over T3 minus TP. Well, what we're finding out here is, if you look at that really closely, that's a slope. It is the slope of this line that we just created. This line is known as a secant line. And that's because it actually cuts through the function, just like a secant and a circle cuts through the circle. It's a secant here. If I'm trying to find this velocity at this point, it looks like it's increasing pretty rapidly here. But looking at this, that looks like a nice flat line, a slow velocity. So I don't think that's pretty accurate. So I'm going to try and get a little bit closer. I'm going to call this one T2. Okay, and we can do the same thing. We can do x2 minus xp over t2 minus tp, and that's going to give me the slope of that secant line. Looking at it, it looks like it got a little bit better, so I'm going to say, what happens if I get even closer? I'm going to call this one T1, and we can do yet again x1 minus xp over T1 minus TP, and the slope of that line looks even better. But we do know, I haven't quite gotten there, the slope that I'm trying to find is kind of this line over here. We know this is called the tangent line. What we are doing, each of these, if I were to put these in order of size, it would be delta T3 is greater than, that was not the right red, that's okay, delta T2, which was greater than delta T1. So as I was getting closer to the point I wanted, my delta T's were getting smaller. What we're really doing there is known as taking the change to 0. We are actually taking the delta T to 0. We are trying to get that change as small as possible to where there is no change. And that's how we're going to find the slope at that point and find the velocity at that very specific point. So that's the instantaneous part of this, is the closer we can get to it, the closer points that you can choose around a point, the better your answer is going to be. So you always want to, especially if you're estimating off of a graph, which sometimes we will have to estimate off of the graph, you want to find the points as close to possible to the point that you want to get the most accurate velocity, the most accurate slope. So I got two little examples that are going to go with this idea of delta t. Okay. So we have an example here. It says the position of a particle of the function time is given by the curve shown over here. So this is what we're looking at. It says first, find the instantaneous velocity at t equals 1.8. Which is that point right there. Well, they were extremely nice for us, and they drew out the little triangle that's going to go with us. Once again, we know that the instantaneous velocity is going to equal to the slope of the tangent line. And just a reminder for all you out there watching this, slope is delta y over delta x. So they gave it to us, and because this portion is the same as this portion, it's a constant rate of change, we know that we can use this right here. So the delta y is going to be, it'd help if I erased all that drawing that I did. That looks like we can choose any point here. I'm going to choose this one because it's on an actual point, so 8 minus, and then we can come to here where we were. I'm going to use those 2 points, 8 minus 4. And then my delta x is going to be 4.5 minus 2. So that gives me 4 over, math, 1.5? 2.5? Mental math and I don't get along. All right, and then 4 divided by 2.5 is 1.6. And here our units were in meters and seconds, so meters per second. So that's going to be our final answer here. So once again, to kind of step you through what I did, I was able to use the triangle they gave us, and I chose a point that was on kind of, a crossbar here. And so I was able to use that point and then the point they gave us to find the slope. So I did my delta y and I did my delta x in order to get me there. So kind of just really quick. So that's what we're doing. And there's some other good questions here. So if we come into it, it says, when is the velocity the greatest? Well, we know that we're looking at the slope here. And so we're looking for when it has the highest slope, or the steepest slope is really what we're looking for. So it's going to be kind of hard to see. We can pull it up and make our own estimations here. Honestly, it looks like where we were, that's a pretty steep slope. This might be slightly steeper. This actually, I think, is the steepest. And so if that is the steepest, I would come down and say around 4. So once again, it asks for the greatest velocity. And so greatest velocity, I was looking for steepest slope. And I believe the steepest slope is right here. So I'm going to say the greatest velocity is at 4 meters per second. Do notice I did talk about some of the, try to find some spots that maybe would have been negative. It's okay, even if this is negative, if this had been steeper, it still would have been the right answer. So when we're talking about the greatest velocity, it doesn't matter if it's positive or negative. We're talking about quantity there. Okay. And then it says when is it 0? So when is the velocity 0 here? So once again, we're looking at the slope here. We're trying to find the slope. So we're trying to say, is there ever a spot where the slope is 0? And I find it right here. As a really good reminder, turning points, that says turning. are places where slope equals 0. So because it's turning around from going to positive to negative, I know it's going to be that. And here we're looking for the velocity. Okay. And then the last one, ask, is it ever negative? So once again, we're just looking for that negative slope. We're going to come over here and find it, and we're going to say starting at 6 seconds. So 6 to 7.2. We can end it there because the graph ends there. We can say that it has a negative velocity, and that's because the slope of this entire portion is negative. So that's also kind of a review of what we did in class to kind of just talk about these different motion graphs and how they work together and being able to analyze them. The other thing I wanted to talk about is, we kind of brought it up, is actually the limit definition of a derivative. So we said if delta x over delta t is the average, then delta x over delta t as t goes to 0. So the way that we write this, we actually write it as a limit. So we're going to say the limit of delta x over delta t as t goes to 0 is going to be our actual velocity, the velocity that we're trying to find. So we talked about that as we went into it, is that it's getting closer each time. So this is what's known as a differential, a differential, and especially you should have talked about these in pre-calculus, but depending on what we did in the last quarter, especially with school shorting, I know that some of you guys who are in calculus this year may not have seen this yet. So the way that it looks, I'm going to zoom in real big here so I can try and use this spot and use this, is that it is the limit, and I use a big L. So when we're doing this limit definition, it's going to be the limit of your function of x plus whatever your change is. So I guess actually I'm going to use t for us. Plus your change in t minus just your function over delta t. And as a reminder here, delta t is going to 0. And if you think back to what you know about math, you can't have a 0 in the denominator. So we're really trying to work out this function in order to get rid of it. And so there's many different ways that we can do this. There's not actually a way to do it without an equation, which is why we're going to do this example that I have down here. So it says the position of a stone dropped from a cliff is described approximately by, and it gives us our equation here, where x is in meters, yada, 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 t is in seconds. The x plus is in the downwards direction, which is kind of cool, and the origin's at the top of the cliff. Find the velocity of the stone during its fall as a function of time. So this one's actually going to allow us to find that equation. We know from the shortcut, we can quickly go ahead and say that velocity is equal to 10t. We know that. That's our shortcut. But like I said, sometimes you're going to do things the long way. And on the physics test, it does like to test your knowledge of calculus. So it might ask you to do something a long way out. So I'm going to show you how we can step through doing this in the limit definition. So once again, the limit definition says that it's going to be delta x over delta t as delta t goes to 0. So that means it's going to be x of t plus delta t minus x of t as delta t goes, or over delta t. So here we actually know that x of t is equal to 5t squared. So we have that. The function here is t. So the hardest part is figuring out what this is. And so it's actually just saying 5 And then instead of doing t, it's a function of t plus delta t. So we're going to say t plus delta t, and then the function is squared, so I'm going to square it, minus just the function, so 5t squared, and then over delta t. I don't really want to deal with this denominator right now because I need to simplify this numerator. So that's what I'm going to do instead, is work on simplifying the numerator. First thing we need to do is deal with this square. So we're going to get 5t squared plus 2t delta t plus delta t squared. So that's just how you do a sum of squareds, minus 5t squared. We can distribute the 5 now. Well, the great news is you're going to notice the 5t squares canceled each other. So now we're just left with 10t delta t plus 5 delta t squared. Remember, it is still over delta t, and that as that term goes to 0. So what I can really do is I can factor out this delta t here. I have 1 here and I have 2 here. So that's going to give me 10t plus 5 delta t, because I had 2 of them there, and then I can plot that delta t to the front over delta t. The really cool thing about that is now those cancel. I've finally gotten rid of that denominator, so I can let my delta t go to 0 now. So I'm going to take this down here. I have 10t plus 5 delta t. We know that delta t is going to 0, so that really gives me 10t plus 5 times 0. Well, we know that cancels, leaving me with just 10t. For those of you guys who've never done this before, my biggest hint is just treat delta t as another variable. Treat it as a y, whatever you want. Some people get really confused because it's t and delta t, but they're two different things. So just always treat it as something different and you're good to go. The other thing that you have to pay attention to is that this definition is in function notation. So when it says x of t plus delta t, notice that I took the function, I replaced t with t plus delta t. So I did 5, and then I replaced it with that t plus delta t. So recognize that this right here is in function notation. And once again, the reason why we're doing this is because we noticed that as delta t got closer to 0, that's how we were finding that tangent line. And so we took that graphical definition and now we put it into something algebraic. Okay. You know what? I'm going to end there. I think that's a pretty good definition, and I did want to show you guys how to do this calculus-wise, and then also that reminder that this original equation, make sure that you're recognizing that when we're just doing a full delta over a full delta, we're talking about the average. In order to find more of the instantaneous stuff, we know that delta x is really equal to v naught t plus 1/2 at squared. We have to use our equations when we're talking about things that are more instantaneous. I'm not going to use this unless for some reason it's specifically talking about the average.